MET 345 Test 3 Review, Section 1, Isentropic Thinking. How to choose an isentropic surface. The best isentropic surface to diagnose low-level moisture and vertical motion varies with latitude, season, and the synoptic situation. There are various approaches to choosing the best surfaces. Firstly, you can go by season. In the winter, your best low-level isentropic surface might be the 290 to the 295 Kelvin range. In the spring, it might be the 295 to the 300 Kelvin range. In the summer, it might be the 310 to the 315 Kelvin range. And in the fall, it might be from the 300 to 305 Kelvin range. You can also compute a cross-section of isotropes and isohumes, or mixing ratios, normal to a jet streak or baroclinic zone in the area of interest. Then you choose the low-level isentropic surface that is in the moist layer, displays the greatest slope, and stays 50 to 100 hectopascals above the surface. A rule of thumb is to choose an isentropic surface that is located at 700 to 750 hectopascals above your area. Some general notes and some disadvantages of isentropic analysis. When we examine a theta surface, we are looking at adiabatic motions. A constant theta surface will cut through many different pressure levels. An adiabatic rising or sinking is occurring along the constant theta surface. Some advantages to isentropic analysis include, for synoptic scale motions, in the absence of diabatic processes, isentropic surfaces are material surfaces, i.e. the parcels are thermodynamically bound to the surface. If you exclude diabatic effects, parcels will move on the theta surfaces. Horizontal flow along an isentropic surface contains the adiabatic component of vertical motion, often neglected in a Z or P reference system, so a height or pressure reference system. Moisture transport on an isentropic surface is three-dimensional. Patterns are more spatially and temporally coherent than on pressure surfaces. Because moisture is conserved in an adiabatic process, isentropic surfaces tend to run parallel to frontal zones, making the variations of basic quantities, such as U, V, T, and Q, more gradual along them. We see weaker gradients of basic quantities on theta surfaces, giving us more detailed information. Some disadvantages include the temporal continuity of isentropic surfaces are disrupted by diabatic heating/cooling. Diabatic heating or cooling causes isentropic surfaces to move downward or upward respectively. Also, do not use isentropic surfaces or theta surfaces in the summer, though Michigan should be okay along with Alaska. Also, the forecaster must choose 1 to 2 isentropic surfaces to analyze in the lower troposphere, and they're not pre-selected like pressure surfaces. Construct an isentropic cross-section along with isohumes normal to the baroclinic zone, and choose an isentropic surface, but stay out of the boundary layer. Next, we'll go over the definitions of moisture parameters on isentropic surfaces: lifting condensation pressure, condensation difference, and moisture transport vectors. So, lifting condensation pressure, or LCP, is the pressure value of saturation. Basically, it's the pressure at which saturation will be achieved. So it's the height. It's the pressure at that height. Next, we have condensation difference. And condensation difference is the difference between the actual pressure and the lifting condensation pressure on a theta surface. This tells us how close to saturation we are. Less than 20 millibars is saturated, and less than 100 millibars is near saturation. Next, we have moisture transport vectors. Moisture transport vectors are defined as the product of the horizontal velocity vector, V, and the mixing ratio, Q. Horizontal moisture convergence, or MCON, is equal to negative del dot V times Q. Remember that del dot something means convergence/divergence. And remember that VQ in that equation is the moisture transport vector. You'll have convergence of the VQ vectors where moisture and lift are maximized. Precipitation will be downstream from the moisture convergence maximum. In other words, wherever there's the most moisture convergence, there will be precipitation downstream of this area. Next, we're going to go over effects of diabatic heating/cooling on the isentropic framework. Remember that diabatic heating or cooling disrupts the temporal continuity of isentropic surfaces. It causes them to move upward or downward respectively. At night, the surface will cool as long-wave radiation is emitted to space, and during the day, the surface will warm. And when it's warmer, isentropic levels will sink or go into the ground. Next, we'll go over the mass continuity equation. We'll explain the terms and how to combine the four terms into two. I won't be reading over the entire equation here, but I will be reading over the term names. So, term A is the horizontal advection of static stability. Remember, you can indicate advection by the fact that it's a vector dotted with the del of something. So, for example, negative v dot del of dp d theta is advection of static stability by the wind. Basically, for term A, you ask yourself the question, are the winds bringing in less stable air or not? And dp d theta will be less than 0 if stable, but it'll be far less than 0 if unstable, so the negative number will be far higher. Term B is the divergence or convergence of static stability, also known as are you bringing in more air. Once again, remember that convergence or divergence is characterized by del dot something else dot another vector, right? And the question you ask for term B is, are you bringing in more air? Term C is vertical advection of static stability. It indicates vertical motion with respect to the theta surface. Diabatic heating is positive, and stability is rising upwards, and diabatic cooling is negative for term C, meaning less stable air is moving downwards. Term D is vertical variation in diabatic heating / cooling. Remember, if it's more negative, then this means it's less stable. And if it's more positive, it means more stable, aka an inversion. Remember that you can combine these four terms. Terms A and B are equal to the horizontal mass flux, and C and D are equal to the vertical mass flux. Basically, the change in mass horizontally and the change in mass vertically. Isentropic vertical motion is most likely to fold near the ground. Next, we have system relative motion. Once again, I won't go over the entire equation here, but I will state what it means. So, the dp dt part, this means that if pressure increases, we will have downward vertical motion, and if pressure increases, we have upward vertical motion. This is just how omega works. Remember that omega is equal to dp dt. Term A of this equation is equal to the local pressure change on the isentropic surface. Term B is equal to advection of pressure on the isentropic surface, and term C is the diabatic heating / cooling term, which is modulated by dry static stability. Theta is not constant in this term and therefore diabatic processes are occurring. Typically, at the synoptic scale, it is assumed that terms A and C are nearly equal in magnitude and opposite in sign, so they cancel each other out. A key assumption of this equation is that the weather system translates horizontally without change in shape or intensity. And remember that anticyclones or cyclones only change slowly over synoptic timescales. Another assumption is that there's no diabatic heating or cooling and that the shortwave does not deepen or weaken significantly. The thermal wind relationship in isentropic coordinates. When isentropes slope down to warm air, the thermal wind is into the paper, i.e. the wind component into the cross-sectional plane increases with height. This means that when isentropes slope up to warm air, the thermal wind is out of the paper. The tighter the pressure gradient is on the theta surface, the more sloped the theta surface is. And bigger slope means stronger winds, since really cold and really warm air are next to each other, which produces a stronger wind aloft. Next, we'll cover positive vorticity. There are some differences between tropopause folds and tropopause undulations. A tropopause undulation is a big scale dip of the stratosphere and tropopause into the troposphere, and it brings in warm, stable air. This warming from the tropopause undulation brings a low downstream, and a stronger undulation means a stronger surface flow. PVUs, or positive vorticity units, are the units we use to distinguish stratospheric air from tropospheric air. And values of these units greater than 2 indicates that air came from the stratosphere. If absolute vorticity increases, then static stability decreases while gravity remains constant. And this applies for when PV is conserved. A tropopause fold, on the other hand, is a small-scale component of a tropopause undulation. If the tropopause undulation is there, then tropopause folds are like branches off this undulation. Next, we'll cover the definition and equation for isentropic potential vorticity, or IPV. IPV is defined by absolute vorticity divided by stability multiplied by gravity. Remember that IPV is conserved for flow that is frictionless and adiabatic. So this is going to be flows above the surface where diabatic processes aren't occurring. It will be created and destroyed in the presence of gradients of diabatic heating or cooling. Stability and thermal properties of idealized positive and negative PV anomalies. Positive PV anomalies are characterized by warm air with cold air below it, as well as cyclonic rotation. Remember that the effect of this anomaly will get weaker the further you go out from it, but the effects will be stronger and last a longer distance if the anomaly is greater in horizontal length or if the area is less stable. Negative PV anomalies are characterized by a bulge upward in the tropopause, and this bulge places cold air above warm air. The area inside the anomaly is less stable, and the area below it is more stable. It is characterized by anticyclonic flow. Next, we'll cover the invertibility principle. The invertibility principle is a tool that allows us to see how much the tropopause undulation or fold is influencing the flow. In a full inversion, areas of tropopause undulation are combined or added together to make one whole. And in a piecewise inversion, we isolate a certain feature of the undulation, or PV anomaly, hence its name piecewise. A full inversion versus a piecewise inversion is like a whole puzzle versus individual pieces. Remember that once again, the two factors that determine the depth of influence of a tropopause undulation are the horizontal scale of the anomaly and static stability. If the anomaly is larger lengthwise, then it will increase the depth of influence. And if the area is less stable, then it will make for a bigger impact. So less stable, more wide means bigger impact. There are two different definitions of the tropopause, the dynamic definition and the thermodynamic definition. The thermodynamic tropopause is defined by the lowest height at which the lapse rate decreases to 2 degrees Celsius per kilometer or less, provided also that the lapse rate between this height and all other altitudes within 2 kilometers does not exceed 2 degrees Celsius per kilometer. This tropopause definition is based on stability, and the criteria are not as physically based. It provides more detail, but detail could be due to gravity waves, which are a mesoscale event and aren't reflective of a large scale. Dynamic tropopause definition is the one we'll most likely be using, and it's a surface of constant IPV, typically between 1 to 2 PVUs, or potential vorticity units. Typically, values of IPV greater than 1.5 to 2 potential vorticity units indicate stratospheric air. A steeply inclined dynamic tropopause indicates that there is a strong gradient of pressure or potential temperature, and this implies that there is an intrusion of stratospheric air into the troposphere, otherwise known as an undulation. Remember that an upper-level positive PV anomaly will propagate westward. This is because the anomaly's circulation will advect high PV southward west of the anomaly and low PV northward to its east. This will propagate the initial anomaly upstream and produce a negative anomaly east of the original feature. This new negative anomaly will have its own circulation and will spawn a secondary positive anomaly even further east. Low-level anomalies, however, will propagate eastward. The net effect of warm air advection downstream and cold air advection upstream is to propagate the warm anomaly downstream toward the warm air advection and away from the cold air advection. So, when considered in isolation, upper and lower level anomalies will propagate in opposite directions of one another. However, do keep in mind that low level and upper level PV anomalies can influence one another, depending on their depth of influence. The reason that these anomalies don't propagate away from each other, however, is that they kind of hold each other in place due to their propagation patterns. Remember, once again, that IPV is conserved under adiabatic and frictionless conditions. And IPV will be created in regions where the diabatic heating increases with height. And IPV will be destroyed in regions where the diabatic heating decreases with height. Remember this from Keeler's class, where we worked with the cloud. So from a potential vorticity perspective, there are three impacts that latent heat release will have on cyclogenesis. Remember that latent heat release is a form of diabatic heating. This will cause erosion of potential vorticity at the tropopause level, which will increase the slope of the tropopause, which means that the slope of the theta surfaces has also increased, and the jet streak aloft has strengthened, which typically leads to increased divergence production aloft. The diabatically produced potential vorticity in the low to mid levels will have a cyclonic circulation associated with it, which will enhance both the mutual amplification and phase locking effects. The latent heat release will increase the depth of penetration of the upper level potential vorticity anomaly through weakening the static stability aloft, i.e. it will warm the mid-levels through latent heating with colder air aloft. So remember that this is a positive feedback process.